Okay. Okay, we're starting now, yes?
Yes,
Okay.
we are starting. Go ahead.
Okay. Well, welcome everybody. This is the Post-Quantum Cryptography panel webinar. This is organized by and co-hosted by the IEEE Future Networks, along with many other IEEE related organizations, which I will acknowledge later. First off, I will start by introducing very quickly the panelists, show who they are, as well as introducing the Future Networks technical community itself, and then I'll pass, and then we'll get on with the core content of this panel webinar. Next slide, please. Okay, with us today as panelists are Prakash Ramachandran. He co-chairs the Quantum Information Technology Working Group. Dr. Eman Hammad, she co-chairs the Security and Privacy Working Group. Dr. T.S.L. Radhika from BITS Pilani in India. Dr. Havas Jiafeng Xie with Villanova University in the USA. And I am Baw Chng. I co-chair the AI-ML Working Group in the Future Networks technical community. Next slide, please. This is my old biography, which I will not spend the time going over. Next slide, please. As a quick introduction to the Future Networks technical community, this technical community is supported by 9 IEEE societies. You can see all 9 listed on the left of the slides there. Within this community, we have 7 committees, and the one that I want to highlight here is the INGR. The INGR is itself a committee. It's comprised of 15 working groups, and on the next slide, we'll talk about that. Next slide, please.
Yep. Sorry. Am I missing something?
Yeah.
Just a second.
That's okay.
Yeah.
While we're on the slide, I point. Okay, that's fine. The INGR working group. So what is the INGR? The INGR is a short for International Network Generations Roadmap. It is a technical document that we revise every 1 to 2 years, where we try to anticipate development and challenges for networking technology, networks, infrastructure, and network technologies for the longer term horizon, meaning 10 or more years. So within that framework, we are organized as 15 different working groups. You can see all 15 listed as bullet points in this slide here. AI-ML is one of them, for example. Security and privacy is one such working group, for example. Quantum information technology is a new one that was created just late in 2024. So these are the 15 working groups. Together, we put together the International Network Generations Roadmap, with short INGR for short, and we revise that roadmap every 1 to 2 years or so. Okay, next slide, please. Now, this is the International Network Generations Roadmap, as mentioned before, is our flagship publication. In the 2024 edition, this is the latest one we have. It has 11 topical chapters. Early editions have all 15. It's just that for the 2024 edition, there are only 11 chapters that has been updated from 2023. So the 11 are listed here. You see 12 cover page because the first one is the executive summary. Okay. So again, it's a technical roadmap that looks at the 10-year plus horizon for network technologies and network infrastructure and network and the network themselves. Okay, the QR code and the link on this slide here will point you to where we make the roadmaps available. Next slide, please. Okay, Future Network Technical Community have as our flagship conference an annual Future Networks World Forum, which for 2025 will take place in Bangalore in India this year, November 10 to 12. You have a link on the screen that if you want to learn more about the forum and possibly register to attend the forum. We have Connecting the Unconnected Summit, and we organize the Connecting the Unconnected Challenge. It's an annual global IEEE competition that solicits solutions from startups, grassroots organizations, universities, anyone else that is working to bridge the digital divide in innovative ways. Now, from the 2024 conference, we noticed that there are immense interest in AI/ML and quantum technology. These are the two most popular topics in 2024. I took some statistics and found that over 1/5 of the accepted technical papers are AI/ML related. There are 2 keynotes that are AI/ML related, 1 symposium, industry forum, 1 topical vertical, 2 tutorials, INGR real sessions, student leadership summit and women engineering sessions, young professional industry and training and mentoring sessions. Many of them, all the things listed here, have AI/ML related content. Next slide, please. And yeah, along with ML, the other most popular topic in the world forum is quantum computing related. For the AI/ML working group, since I'm the co-chair, I will briefly introduce that working group. We're part of the Future Networks technical community. We provide roadmap based on research and industry advancement to deliver the AI/ML vision for the networks of the future. We care about AI and machine learning as they relate to networking and telecommunications. We care about architecture and frameworks to support AI/ML workloads for different domains. And most importantly, we anticipate AI/ML challenges and developments over multi-year horizons. Again, for us, that means 10 or more years. We organize things like webinars, industry outreach, forums, conferences, etc. For the AI/ML working group. On average, we do one webinar or so per month on average. And sometimes we get that co-hosted by other IEEE organizations, for example, the Philadelphia section, and in this particular case, the Quantum Information Technology Working Group, as well as the Privacy and Security Working Group. There's an email address on the screen, which you can use to connect with the working group if you want to join the working group or have inquiries for the working group. Next slide, please. And here we acknowledge our co-hosts and our co-sponsors, the Emerging Open Tech Foundation, the INGR Security and Privacy Working Group, the INGR Quantum Information Technology Working Group, the INGR Artificial Intelligence and Machine Learning Working Group, the IEEE Philadelphia section, as well as the IEEE Computer Society Philadelphia chapter. So we thank you all, our co-hosts and co-sponsors. We have a bunch of seminars scheduled for this quarter. So we're now at September 11, talking about post-quantum cryptography, but coming up next, we have on September 18th, a talk on automated LLM-driven scheduler generation. September 25th, that one is still TBA. October 2nd, another quantum-centric topic on quantum machine learning, quantum architecture search by Dr. Samuel Chen. Registration link is already live there. Feel free to take a screenshot if you wish. October 9th, TBA. October 16th, another one coming up. Also quantum related. It's on distributed quantum neural networks on photonics, distributed photonic quantum computing. That's for October 16th. Not this on the slide, but we can go back and add it later. Right. Next slide, please. And with this, do I return the floor to you, Prakash, or Eman will take over right away?
Okay. Definitely, Ima can take over, but I'll just introduce her, saying that she's the Security and Privacy Working Group co-chair. She's the electrical engineer, PhD electrical engineer from University of Toronto, and she's one of the top cybersecurity professional, and she's assistant professor, and her details are there, you can see, but definitely you can hear from her. And with that, I'll hand over to Ima. Ima, go ahead. Are you the presenter? Or can you
don't worry. Don't worry about it. Just let us
Okay. Speak. Thank you, Prakash. Can you hear me well?
Yeah, we can. Sure, go ahead.
Next slide, please.
Mm-hmm.
Okay. So what, as Prakash mentioned, I'm the co-chair for the Security and Privacy Group in the INGR effort. I've been volunteering there for a couple of years now. I've been working in cybersecurity for a number of years. I wanted to start by looking at the shift in the threat landscape, given that what's happening right now. What you see on the top right corner is a recent news from the past few weeks where a Google researcher anticipated that the time to break RSA 2048 will be something that's achievable or feasible within a week with less than 1 million qubits. And that was anticipated, and this is why we're having this seminar. So I wanted to motivate this seminar a little bit forward. Another news was earlier this year when there were claims that some scientists already were able to break RSA. That was proven not to be the case, but I think given where we are right now, that's not far into the future. What we are observing also from a cybersecurity perspective, that we have increasing sophistication of threats. We're seeing more like a business type of approach, like organized crime, or following a business as a service for ransomware, for different services, for foothold, for reconnaissance. So the security stack is getting more complex on the defender side, but it's definitely getting more complex on the adversary side as well. The cloud transformation, where everything is in the cloud, is providing more, is proving to be more challenging, specifically from the point of risk monitoring and management. And we'll talk a little bit more about risk just as an education, like maybe like a brief intro onto how we look at it from a cybersecurity perspective. It's a fact that we have a huge talent shortage when it comes to qualified, able, capable cybersecurity workforce. So that leaves many of the businesses in the reactive mode. And this is why when we talk about post-quantum, the deployment, the transition into post-quantum cryptography, whether for data transit or data at rest, it has to be something that's usable. It has to be something that's practical to deploy and test and monitor. Also, we are seeing more of the AI-driven threats and attacks, similar to the one I just talked about. So we have now what we call the war of algorithms. So we have AI against AI, and one of the tools will be trying to break any encryption there, or try to harvest side channel leaked information to maybe they do not need to break the encryption, but they can still glean some meaning of what's going on. Next slide, please. Okay, so in the security and privacy group, what do we do under IEEE? We endorse a philosophy where we look at systems and we say we want systems that are secure by design, are resilient by design. And specifically, when we look at next generation networks, we're looking into how we can ensure that the security by design is something that's feasible and can be deployed and can be monitored. And we follow that through two venues: assessing existing solutions, and as Chao mentioned, we try to look into the future with a horizon of 5 years or 10 years and say, okay, those are some of the anticipated changes that we look at as IEEE, and this is our assessment of what the risk could be, the risk profile could be, and what are some of the approaches. Now, granted, the 10 horizon is becoming harder and harder to target because of the rate of change in technology and the threat landscape, but still on the short and medium horizon, that's something that we target to do. Another thing that's corner to our philosophy in the security and privacy group is to adopt a challenge versus opportunity thing. So wherever there's a challenge, there is also an opportunity. One example is complexity. So we know that the future networks are more complex, and this is why AI-ML is a pillar, like a critical pillar to enable operational effectiveness. At the same time, that is also an opportunity from a cybersecurity perspective. How can we leverage that complexity to make the system resilient by design? So we have many degrees of freedom. Let's look at it from the brighter side. At the same time, we did establish in the chapters, in the different versions of the chapters, we have, I think, 4 editions right now, a systematic taxonomic approach that is aligned with the state of the art and the standard within the cybersecurity community. Next slide, please. So as you can imagine, when we look at the 6G and next generation networks, we are, as a cybersecurity group, we're looking into security from a system perspective, and that touches multiple layers. And I tried to highlight here the quantum safe security as one of those layers that we're looking into. Next slide, please. Just for an example on how complexity and what the threat landscape looks like, this is for 5G, spelled out the connectivity from the user equipment to the cloud providers, like app providers, going through the RF, the G-Node Bs, the transport layer, and the core of the network. As you can see, there are multiple points where possible threats can aim to try to infiltrate or affect the network, whether it's on the virtualized network functions or it's on the transport layer, etc. Cryptography proves to be a key aspect. Cryptography in terms of supporting identity, in terms such as hash functions, as I'm sure other speakers will talk about, as also as a mean to obfuscate or mask the input in terms of encryption. Will be a key feature when we talk about the protect function. Next slide, please. So just a helpful hint when you talk to anybody who works in security, this is how we think about the world. So the most valuable asset is data. And when we think about data, what could harm data, we think about confidentiality of data, integrity of data, and availability of systems that handle the data. And as you can see, confidentiality from the definition, it's self-explained. Cryptography fits right in because that's a key capability that supports confidentiality. Integrity at the same time, hashing or digital signatures, and cryptography is a key enabler as well. Next slide, please. Some of the definitions that we use are the cyber threat. Cyber threat is not equivalent to a cyber attack. Cyber threat is the potential harm. So it's an adversary that is equipped by tools and tactics and techniques, and they're aiming to cause some impact. So it's the actual risk. A vulnerability is a weakness, and the weakness could be in the system itself or in the capability, the security capability that the system is using. So to translate what we're saying, so most of the encryption functions that we're seeing right now will be vulnerable to an adversary that's equipped with a quantum computer, for example. Risk assessment is the process to evaluate all of this. So we have assets, we have data, we have systems, we have communication in transit, and we are thinking about the adversary, the capabilities of the adversary, and we think about the system and what's available at the system level to protect the data. And then we evaluate, is this something that I should be worried about or not? Next slide, please. So because it's very complicated, we always need a framework to start thinking about this. And one of the most common frameworks is the NIST cybersecurity framework. This is version 2.0, which brought governance as a key component, a pillar that cuts across the key subcategories, which are identify, understand what the assets that you have, understand what the risks that could target them, understand the risk scenarios and the threat actors, then protect, identify what you can afford to increase the security of those systems in terms of the CIA, confidentiality, integrity, and availability. Then if anything goes wrong, are you able to detect? And if you detect, do you have the capability to respond? And if you respond, whatever your response is, are you able to recover those systems? And it's a loop. Next slide, please. So how do we assess the risk and what can we do when there is a risk? That's something that humans by default, our brains are wired to do risk assessment all through our lives. When it comes to cybersecurity, it's not anything different. We look at what could happen. We have we have like a traffic light in our brain. Is it green? Should I be worried? Is it yellow? Should I monitor it? Is it red? Should I do something about it? Next slide, please. And this is how we translate this as a risk register in any company, in any solution, in any technology. We have this mapping of those risk scenarios, and we have to decide whether we want to accept the risk, whether we want to transfer it, whether we want to reduce it, or do we want to avoid it altogether by changing the system or changing the business or changing the technology, etc. And here, what's key to understand when we assess the risk, two elements. One element is the likelihood. Is this likely to happen? So if we're talking about a threat actor that's equipped by a quantum computer, is this likely to happen? And the answer is yes, because we're looking at organized cybercrime, getting more and more accessibility to state-of-the-art resources. The risk impact, like what could happen if this is true, the likelihood is high, likely, or almost certain, then I look into my system and say, okay, what some of the key cryptographic scheme that I'm using, are they quantum safe? If they're not quantum safe, what degree of complexity, what additional measures am I taking? Next slide, please. And this is a flow chart that walks you through those steps. So I identify the threat source, the threat event. This will exploit a weakness in the system, and then based on that, it will cause some adversarial effect or impact. And this gives me the risk rating if I walk through this as a mock play or an exercise, tabletop exercise. Next slide, please. So as any asset owner, whether it's you as a person or you as part of a company or organization, this is a helpful flowchart to go through. So I understand, identify, protect, detect, respond, and recover. Next slide, please. Okay, so I wanted to put this out there to help with the discussion afterwards. So what are, from our side, what do we see as possible challenges in post-quantum encryption adoption? Key things that when we're looking at encryption in general from a security perspective, we really care about what's the overhead to implement encryption. So for post-quantum, a key characteristic, they have larger key sizes and they have higher computational overhead. So which could impact the systems that will be compatible with those algorithms. So we're specifically talking about IoTs, some of the more constrained resources, IoT devices, embedded systems, and legacy systems. Efficiency trade-offs, if you have those algorithms that are resource heavy, that will require a finer balance between energy consumption and processing speed, especially for critical like latency sensitive applications. From a standardization and integration perspective, those standards are still evolving. And I think today we're going to go through some of the FIPS and the standards that are already reaching some point where people are able to implement. But this does not dismiss the fact that this is still happening. This is still going on. So from a deployment perspective, it makes it harder. Complicated systems and protocol transition. So it's a fact that if we want to get this into TLS or passkeys or any of the capabilities that we have, it will take time to actually transition and test its applicability, scalability, etc. But it does put us in an interesting perspective where I think most institutions are faced with this question. If any algorithm, not just post-quantum, it's not a quantum problem. If we want to roll out some encryption algorithm that we have right now because there's a vulnerability, are we able to do that with a certain level of agility? Can we actually go through the whole system, most of the components, really know where this is applied, and really have a process to actually roll a new algorithm and replace the existing algorithm, which is something that we need to face and we need to develop the playbook to do. I'll skip the supply chain organizational barriers because that's a governance issue. More onto the new attack surfaces. So post-quantum does not necessarily solve that. It's still, as encryption in general, is still susceptible to some side channel or implementation specific attacks. So it's a layer underneath the post-quantum. Also long-term data risk. So we evaluate the risk of post-quantum as high or moving towards, trending towards high, because we think about the time to break a cipher. So we're saying, okay, we're transmitting this sensitive information and we're worried that somebody will break it in a time before we change the key or something like that. But some crime models are following harvest now, collect the data now, and you take your time to decrypt it, right? So does post-quantum change that perspective? And thank you, I'll pause here.
So thank you very much for the security and privacy groups perspective, and the references are here. Now we'll move on to Dr. Jiafeng Z. I think, Baw, if you can introduce, that will be better. Baw, are you there?
Okay, yes.
Yeah, go ahead.
Yeah, Dr. Jiafeng Hammad. He received his PhD degree from the University of Pittsburgh in 2024. He is currently with the Villanova University near Philadelphia in the USA. Dr. Xie's specialty includes homomorphic encryption, cryptography, fault detection, and digitalization for telemetry systems. With this, Dr. Xie, please take it away.
Okay, thank you. Thank you so much for the introduction. I just want to give you guys a little bit more ground on what's going on with the post-quantum, the history or whatever. So I put here the slides here. You can see on the right side that this is a quantum computer possibly being built. But so far, the thing is, has been approval in the, at least in theory, say that RSA and ECC will be vulnerable to the quantum attacks in the next, I'm still thinking about 10 to 12 or 15 years. So this is kind of a time frame. And in fact, I think like the US government, they are setting a deadline that's 2035, say that the government has to transit to quantum resistant cryptography. So I'm thinking about maybe 2035 will a critical time, but we still have several years to go. But that does not mean that we are safe. We still, because from crypto system development perspective, it really takes time, to finalize a mature scheme before the very powerful quantum computer becomes available. Next slide, please. Okay, so the reason is very simple because of Shor's algorithm. Okay, so he's Peter Shor. He's very famous, but so he creates a very nice problem for us to solve. So that means that the existing RSA and ECC, they rely on the integer factorization kind of it's basically their the cryptographic problem was built, but this problem is vulnerable in the quantum computing kind of scenario when Shor's algorithm is executed. But the good news is still, although there are companies claim that, oh, we have, certain qubit level quantum computer developed, they are still not powerful enough to really execute Shor's algorithm and to break RSA and ECC. But let's wait and see what's going on in the next few years. But okay, next slide. So the next slide is talking about, there are various kinds of post-quantum cryptography. I think that the beginning idea of PQC was originated in the early 2000, actually. And in fact, the first international conference on post-quantum cryptography was held in 2006, okay? So this is, at that time, people are still trying to figure out if this is real or not. I still remember that, some people, they tried to do research on the post-quantum cryptography. And then the others, they were really questioned by the others, say that, is this a fake topic or not? Okay, so that was the, that was the situation. And the last time, even during kind of NSF PI meeting, I met with a lady, and she's doing research in applied cryptography. She's also very curious about post-quantum cryptography. Will this be real or not? Or it's still kind of like potentially, quantum computer will never be realistic. But as time goes on, I think this kind of concept is gradually and fading away. More and more people realize that post-quantum cryptography is urgent, is needed. Okay. Along with this line, there are multiple PQC schemes and problems were built by the research community. The most prevailing one probably is the lattice-based, but they are code-based as well, hash-based, multivariant, and isogeny, etc. I think according to the NIST standardization, thank you so much. Kind of like at the timeline and the milestone, we can see that in 2016, okay, they announced the first round of call for submissions. So at that time, actually, there were about 69 submissions, okay, considered as complete and proper. Then the second round started to be available at the time of 2019. Actually, I still remember that. One of the reason is at that time the NIST they start to looking for people who can do some research, implementation research on the second round candidates. That's the early 2019. Okay, and then during the pandemic, there was kind of I cannot remove that from my memory. I still remember there was the summer of 2020. And I was trying to go to bed, and then something pop up on my cell phone, and then I realized NIST just released the wrong candidates. Okay, and I was so happy to see that because at that time we were involved with one of the schemes, tried to do some research on that, and that scheme also was included one of the final candidates. In the third round, but it was really in the midst of the pandemic. Everybody was locked down, but that site was not locked down. Okay, so eventually, at the year of 2022, July 5th, okay, there was still also a kind of like a very striking kind of like a date for me. The reason is that I thought, because of the somehow original they thought is they gonna release the final result in the spring of 2022, but then something happened that it was delayed. So I thought they gonna announce it maybe later in the fall, but all of a sudden in July 5th they released the final candidates to be selected, and also the first round candidates. And of course, in July 17, 2023, NIST also announced additional digital signatures candidates. Okay. So along with these lines, there are 3 FIPS released, then, 3 FIPS then finally approved, then first round algorithm is selected. So along with this line, I would like to say that if you really want to see what's the trend, you can read one of my paper published in 2024. That's called Hardware Circuits and Design for Post-Quantum Cryptography. It's a tutorial brief published in IEEE Transaction on Circuits and System 2. So that paper is open access. You can very easy to find it. So it gives you all the details and also all the trend. What's the recent trend and what's supposed to do after this. Okay, next slides. So among these NIST select PQC, I would like to mention that Kyber and Dilithium, they are both built on the module learning with errors. Okay, so the reason I think why they choose this module learning with errors is one side that they provide flexibility in switching different kind of modules and to realize different security levels. On the other side, it's module learning with errors is kind of in the middle between the ideal ring learning with errors and the original learning with errors. So they kind of needs to pick them in the middle. So it's kind of like the original learning with errors probably is a little bit complicated, but module is ideal is is very, very ideal in terms of complexity. So they just choose in the middle. This is my thinking, okay? But then the original they thought is they're gonna choose between DILIsm and a Falcon, but then they realized that Falcon also has Falcon. This algorithm is very difficult to understand, to be honest, and I don't think there are many people who can really understand Falcon. Okay, so if you want to read some how Falcon works, you can also probably refer to some of my papers. I published a couple papers related to, especially implementation work related to Falcon. You may look at them and you will realize how complex the algorithm it is. But the good benefit for Falcon is its digital signature verification is very fast. It's the fastest, okay, among all the PQC schemes. Phoenix Plus is a hash-based. So this was later on also selected. NIST choose that as an kind of like a alternative solution. HQC, okay, so it's one of my favorite scheme because I also did some work on that. And the original HQC was not as the top priority. People always think bike gonna be chosen, but eventually HQC outperforms the other schemes. And by the way, so Falcon probably will be standardized after 2 years. The additional digital signature scheme is still ongoing, so it's now it's in the second round. So you guys may look at the details and try to see what is going to happen. So I probably have to briefly just stop it here. Before I go, I want to mention that yes, this year's the sixth PQC standardization event is on December 24th. Okay, so if you still have time, you can register for that, and you may just go in person as well. There will be very interesting presentation. I also have a presentation there, so hopefully I can also see you face to face there. There are many interesting things related to the PQC standardizing process, especially relate to the hardware implementation and related security topics. All right, okay, I may stop here. Thank you so much.
Thank you very much, Dr. Harvest. And I think harvesting and decoding is the key. So we cannot forget you. Hopefully, some of us can meet you at the Maryland conference. Going on further, my background, I have been a generalist and I have been working on the 5G earlier, now moved to the quantum some 5-6 years back, and I've been in the Valley, Silicon Valley, for a long time and worked for various companies, which include Dell, Huawei, AT&T, and various other things. So I'll move on with my qualification, what I have. Best I can provide you some insights into this. So one of the things we have to look at the impact of the cyber attack. And so if you look from the statistics provided by CSIG, which is the Cybersecurity Information Group, what they say is probing attacks are nearly half and payload attack are roughly quarter. And remaining attacks are like denial of service, trying to use remote as a user local and user trying to get into the root attacks. So those are around 7-8% each one of them. So what it means is the probing attack is one of the major ones. So a simple probing, like example, today we heard that in Russia tried to do something and probing in the sense that you got Poland attacked. So it can be very deceptive. So probing is one thing which we have to watch. And then, of course, if they get into the payload or like inside out or outside in, whichever way type of attacks they do, they will have to make sure that we are able to cover them. And this does not depend on the size of the nation. It can be any small, big, wherever there is a critical thing, this can happen. So adversaries are all over and one has to protect oneself. Now, we may have the stats, what I read in one of the IEEE magazines, they projected as both Dr. Harvest and Dr. Hima pointed, the FIPS 203, of course, Crystal is very important. Crystal is, it's a cryptography suite of algebraic standards. So we have to look at crystals is a suite which is a code based, and then that provides the procedures or algorithms, and these are standards which we need to adopt. And the FIPS 203 is a general encryption standard, and it's for encapsulation encryption, and this uses lattice cryptography. So does FIPS 204, which is dilithium. So both are similar, but one of them is for digital signature, one is for general encryption. And this is again lattice based, and all these are available. FIPS 205, which is Sphinx, plus I am putting plus 3.5 because there were some feedback, and accordingly they removed those what do you call the objections or whatever they have come across. That is a digital signal, but this is hash based. So the idea is that you do have lattice based as well as hash based. And FIPS, I don't have to explain. You saw I put it as Q4 2025, but it looks like it will be 2026. So because I am unaware of the latest and which Dr. Harvest mentioned. So these are the quantum crypto standards, new ones I would put it. Older ones were there already, we know that. And the only difference is they were called, for simplicity, Kyber and dilithium, but they have been made modular, and so they call it modular lattice ML-KEM and similarly ML-DSA. Both are based on lattice, and these are meant for the post-quantum cryptography, safeguarding both classical and quantum attacks or through attacks. So you can see here quantum resistance KEM. So there are two terms you take away from here: KEM, key encapsulation mechanism, and the other one is DSA, which is the digital signal, digital signal signature authorization. So KEM and DSA, these two are the key for digital safety, because we deal in digital assets most of the time. Of course, digital assets also include embedded and hardware, software, and all. So the key is the important part is, if you have key, there is a common key, and if there is a common key to be used, that has to be exchanged, and then it has to be encapsulated and delivered to the two parties, A and B, let's say Alice and Bob as we generally refer. And quantum security, to against the attack from quantum computers, we need to, or quantum computational means, we need to defend. And so the Kyber and the Kyber, let me continue. Dilithium will come later. So Kyber, what you have is example, very simple. Of course, all these references, when I say SP and FIPS is the Federal Information Processing Standard, and special program or special projects, SP gives you the documents. So in the case of key establishment, Alice sends a encapsulation key to Bob. Bob encapsulates and returns the cipher, and then Alice decapsulates to generate the key, and so does so this is called key establishment. So key establishment has three. One is key generation, and that key generation requires some inputs. Like example, you can use a pseudo random number generator, or you can use a quantum QRNG or quantum random number generator along with this whatever seed, and whichever way, either you do software or hardware, you generate the key at a place. If Alice generates it, then she shares with Bob the information, and Bob takes it and returns the cipher, so that decapsulation is the most important thing, because most of the time DK is a private key, you can call it, whereas encapsulation key is generally public. Depends on whether you are using PKI or even similar things are happening there. So there are symmetric and asymmetric. So this key establishment process is very defined, and you can also combine. It's to protect against new stuff, somebody trying to break it. So you can use two keys and two ciphers and combine them. So there is a combination you can apply. So there are various standard SV800 227. I think it's not 0227. There is a typo there, but you can understand that hybrid PQC is also allowed. It depends on what is your goal. That is, as an organization, what do you want to achieve? Whether, like CIA mentioned, the confidentiality, integrity, and availability, and there are medium, low, and high, and how do you rate it? How do you want to achieve those categories? You can have different combinations thereof. So here you can also combine the two keys and make it work together, but all this has to be based on the process that is defined. So you cannot use arbitrary things. There are some recommended things, and there are steps in that, and like you do a salt to the password by adding something to deflect. There is similarly for encapsulation, you do some through cipher. So these are some of the inputs that you can use, but this cannot be arbitrary. It has to use a standard, and the standards mentioned in FIPS are all pointing to this 856C for key derivation, and one has to adopt one step. There are not just one way, there are alternate ways. So you can use the requirements for FIPS 203 is there are something like 12 requirements and 2 mandatory. So there are some requirements which are shall and which are mandatory. So you can see them for every one of them. They have a section in this FIPS document stating how do you manage. So, and not only that, whenever you have a key defined, you need to have a certification. You can't just arbitrarily use anything. So there is a process called CKMS, that is cybersecurity key management services, and then that can be also be federal based. So FCKMS, all these are run through various certification programs called CVPA, and so it can be for algorithm, it can be for the process. So this I don't have to go to run through this, but just to give you, there are profiles you create, and then you apply the security policy based on the roles and responsibilities, and then you can use the metadata and interoperate. And so these are the various things for assessment and challenges and how one can overcome. So KEM, as I said, this is three process. You have keygen, you have the encap and the decap, and this can be done not just by Alice. It can, every owner of a key has to do it. Like Bob wants, then it can be done at Bob's end. If Alice wants, they can do it. So each one has their private key preserved with themselves, which is never disclosed to anybody. Otherwise, the encap decap process keeps going, and these are the standard ways. This is a simplified view showing that it's a probabilistic way of doing it. It is not arbitrary. The only thing deterministic is decap, and that is why one has to ensure that the person who owns is able to or the organization that holds the key is able to decipher it to the accurate to the nearest possible, depending on it's integral. If it's integer, then integer. If it is fractional, then so depending on what accuracy you require, and this can be done. And this is a simplistic view, but this gives you the big picture. And I would skip this because this is nothing but explanation of the same what we did in figure 1 here. Next, I move on to DSA. Now, DSA, digital signature authorization. Normally, now what we do is we used to use the PKI public key infrastructure, and then we sign certificate of signing and all. And then, if you want, you have your sign registered through third party and all that. Now, the one thing about hash is that hash function, it should be one way. That means if you have something which you like, example, when you do a digital signature, you go on your mouse and create a random pattern, and then it generates a key, and then when you use that signature, you can encrypt and decrypt. But the hash, important thing is you got a longer input, which could be we call it as bits or bytes. So usually in terms of security, you call it bits. So whatever bits you generate, but on the other side, hash is always a one way. In that sense, you can have any input, but it should generate the same thing. Then only it is. Otherwise, it will be conflicting. And the other thing is collision. Two different people using two things cannot generate the same map, so it should not produce the same output. So these are the two key for hash function, which are available on SP 889. You can go into the details of it. And this is the hash function simplified view. So you got the message. Of course, the terminologies are a bit hard, but to remember that in digital signature authentication process, sometimes they call it DSA as algorithm, sometimes they call it authentication. But nevertheless, the whole process is you generate the signature, you verify the signature, you use the message data, and then apply the hash function and provide the data to the public or to the people who need to have, and then they can validate it. And once they validate it, they can. So private key, public key. Public key is the important one which is available to public, but private keys are the secret keys which needs to be preserved. So this is the process, and the flow is very straightforward. I don't want to get into the explanation, but assurance is very important. Whatever you do, you need to assure that it is correct, and therefore you need to follow the FIPS process as well as SPs which are mentioned, and make sure that you follow those processes to get the assurance that whatever you are signing is perfect, and then it is not being hacked or cracked by any attacker or adversary. So that's the key to process. And this is the simple 5-step process which I am taking for stateless hash DSA algorithm. It can be for any other, but all of them include a key generation, a signature, a hash function, and then verify that what you have done. And obviously the public key PK is important, and that is why I mentioned, because there is always a confusion. What is this? Pre-hash function is a random function, signature. So public key and the private key is the your signature shared secret. So this needs to be preserved, and the various functions are available and codes are available, and I think I'll pass on that later to Radhika, who's follow up on that. So these are the references, and the math behind PQC, I should ask Dr. Radhika to proceed on this. Thank you.
Yeah.
And her background, just to give, she's from BITS Hyderabad, even though we call it BITS Bilani because that's the main campus. And she's a doctorate in math, and so you need definitely, and she has worked in fluid dynamics, which you know is key. There are a lot of mathematical equations, and she has been teaching quantum computing at her Hyderabad campus, and so I would pass on to her the detail. Yeah, go ahead.
Yeah, thank you, Professor, for your nice introduction. I thank my previous speakers for introducing the key concepts in such a way that my life is going to be very smooth now. Like I can just make the things happen very nice. Like yeah, so yeah, I'll just take you all through the mathematics as Prakash sir has pointed out already. So this post-quantum cryptography, all of us know that it is a quantum-proof cryptographic algorithms. Right, next slide, sir. Yeah, so this is how a cryptography scenario would look like. It's just for all of us, like people who are new to the system. Like we know that we have two parties, Alice and Bob. They just want to share some message between them, and the process would be like this. They have Alice at one party, or Alice will have a plain text to share, and then she encrypts it using certain key, and then she sends a ciphertext to Bob, and Bob uses the decryption key to recover what the text that Alice wanted to send. This is just one scenario, but as Professor Prakash sir has said, Alice would generate an encryption key and send it to Bob. Bob will do this ciphertext part. He will encode the text and send it back to Alice, and that also is a way of doing the things. Okay, but in general, this is how the two parties would work to share secret messages. Next slide, please. Yeah, so coming to the key stages, because the text is going to be in terms of letters or numbers, whatever it is, we try to convert them into numbers. And then we have this encryption or encapsulation process followed by the cipher text generation. And then we have this decapsulation, which finally gives us the original text that the two parties wanted to share among themselves. Next slide, please. Yeah, I'll just take the first, I should say the basic or the first generation mathematical algorithms, how they worked. Let's suppose if Alice wanted to send the message GO. One thing is that she has to write these letters into words. So we have used this ASCII code, right? ASCII code. So for capital G it is 79, for capital O it is 79, I'm sorry, 71 and 79. So she generates this X, the vector X, which is 71, 79. And then she picks up a matrix, because we know that a vector multiplied by a matrix does a sort of transformation. So nicely, they'll multiply this matrix A with X, and then find out this vector B, which is going to be the ciphertext, and that is being shared to Bob. And then what Bob does at his end is he will just calculate the inverse of this matrix, and then finds out the text that Alice wanted to send to him, right? So in this process, both Bob and Alice have to have this matrix A, where the Alice uses the matrix A itself, whereas Bob uses the inverse of it. So in a way, they have what is this symmetric key distribution happening here. Next slide, please, sir. See, in this example, I have just taken a 2x2 matrix, but we can also have a 3x2 matrix for encryption, in which case the encrypted vector would be of length 3. And yes, please click on Professor. Yeah. So in that case, A would not be a square matrix. And yes, we have very robust mathematical techniques to find the pseudo inverses. And moreover, if the length of the text is very large, say of several bytes, this matrix A has to be a very large matrix. So therefore, it's computationally expensive to calculate the inverses and all, right? So and moreover, though we have the pseudo matrices and all, which can play a very nice role in this encryption decryption process, because we have very good methods to find the inverses of sparse matrices, which use the pseudo inverse stuff. So, but then it's always advisable to have a very what should I say, a good matrix A, not always a sparse matrix, right? So yeah. So what mathematics have we used in the previous algorithm? It's a simple mathematical stuff where we have used vectors to represent the information and a matrix to do the transformation, right? And then the operations we used were just a matrix vector multiplication, sometimes little of the vector addition if needed. So that those are the simple mathematical things that we have used in our previous algorithm. Next slide, please, sir. So the mathematical theories behind these vectors is we cannot simply choose any vector just arbitrarily. We have to have certain mathematical background for those vectors, in the sense that there should be some theory supporting those vectors. Like if I do some operation, the resultant vector should not have a completely different behavior from what I have taken to work, right? The initial vector. So therefore, this vector spaces is one particular I should say, a basket from where we'll choose the vectors. So basically, a vector space has some set of vectors, so it's a set of vectors, and it has certain properties that it is an abelian group with respect to vector addition, and it is closed with respect to scalar multiplication. It satisfies certain distributive properties. If you have some basic understanding of these things, that's wonderful. Otherwise, you can just go through this at a later point of time. So the last line, I have a small example where I have taken the set of all ordered pairs, that's a pair of real numbers, and this can be regarded as a vector space with respect to the component-wise addition. The usual way in which we add two vectors, and then a scalar multiplication, multiplying a vector by a scalar. So other related concepts that we have to know, because as we move on, the theory, the mathematics that we require and understanding the post-quantum cryptography techniques, to understand them, at least we need to have some basic idea of these concepts. So that's the reason why I have put all this before we move to this PQC techniques. Right. The next definition is a spanning set. Basically, a spanning set is a toolbox of vectors, and you can build any vector in the space using this toolbox by having a linear combination of them. Next slide, please. So, for instance, here, if you see the left-hand side graph, we have taken the two vectors as 1, 0, the arrow colored red, and this 0, 1 is the vector which is 0, 1 vector is blue arrowed vector. So if I take these two vectors, any element in this R2 space can be nicely spanned by this, in the sense that suppose if I want to say, can I write 2, 3, the point 2, 3 as a combination of it? Yes, it's possible. 2 times 1, 1, 0 plus 3 times 0, 1. Right? So therefore, this set, in fact, you can take any other example and you can see nicely it can be written as a combination of these two elements. So therefore, this forms a spanning set. But if I go to the right-hand side figure where you have just one element 1, 0, if I want to see whether it spans the entire of R2, of course it's not, because if I want to write 2, 3, right, I will write 2 into 1, 0, but there is no space for including 3 into that, the second coordinate. So therefore, this 1, 0 doesn't span the entire of R2. So that's how we understand what a spanning set is. Moving on, next slide, sir. So this is another important concept about linear independence and dependent vectors. Independent vectors, they point in different directions. There will not be any redundancy, whereas the dependent vectors, they don't add a new direction. This is one way of understanding. I'm not going much into the mathematical definitions and all that stuff. Next slide, please, sir. Yeah, this is a graph which helps us understand what an independent set is. To the left, we have this blue arrow and red arrow, these two vectors. They form linearly independent because they are in two different directions, right? There is no redundancy in the direction. Whereas when you see the right-hand side graph, this 1, 1, 2, 2 are pointed along the same direction. So therefore, they have to be treated as linearly dependent vectors. And this is another important set that we will be working on. It is a smallest toolbox which contains the vectors that have the spanning property as well as the linear independence property. Next slide, please, sir. So if you see the right-hand side, we have an alternative basis R2, 1, 1, 1 minus 1, and towards the left, I have the standard basis. So these are not only the spanning set, that means every element in this R2 plane can be nicely written as a combination of them. Not only that, these two vectors are in two different directions, indicating that they are not independent of each other. Yeah. So now let's move on to the pre-quantum algorithms termed as classical algorithms. And the existing public algorithms, they are depending on three mathematical problems: the integer factorization problem, the discrete logarithm problem, and elliptic curve discrete logarithm problem. Of course, the second and third problems can be clubbed together and say it is discrete logarithm problem only. The basic principle behind these algorithms is computing the function is easy, but its inverse is hard. So for instance, suppose if I have two numbers, 2 and say 3 and 7, right? And if I multiply them, 21, right? So if 3 into 7 is equal to 21 is easy to do. It's just a toy example. Don't say that 21 can be nicely written as 3 into 7. The other way, writing 21 as 3 into 7, I'm not saying it is hard, but if this 21 happens to be some 50 or 100 digit number, writing down as a product of two individual numbers is really hard. It's a very hard problem. So therefore, this is the basic idea behind the integer factorization problem. So let me just take this example of Alice sending the message GO to Bob, and how do I convert this into the integer factorization problem? Right. So, so Alice wanted to send GO to Bob, but then, what she does is she will identify the ASCII codes. So rather than sending this 7179 as a vector, which is multiplied by a matrix, the first algorithm we have seen, right, using all matrices. Instead of doing that, what she now does is that she multiplies both these numbers, and then 5609 is a ciphertext which she sends to Bob, right? So now, unless P and one of these P or Q is known, finding out N is really very hard. So that is a basic idea which this RSA algorithm is based on, right? So unless one of these numbers is known, it's really hard to find out the other factor. So that is how this integer factorization problem works. Yeah, so next slide shows the different mathematics that we require, the mathematical concepts that we require, because we have seen that initial matrix method, I should say. So it involved only matrices and vectors. But when you want to work on this integer factorization problems, of course, you need to know about the integer arithmetic. That is not very difficult to go about. And then you see that there is RSA, the algorithm, which is based on this IFP. And then there are the several classical methods to find the factors. The classical attacks are also shown on the slide. Now, the second problem is a discrete log problem, where the problem is to solve. You are given the question h is equal to g power x mod p, where h is known to us, g is known, p is also known to us. The problem is to find x. Okay, so this is not a very easy question, right? And in order to understand this particular notation, maybe we need to know a little of this modular arithmetic, which I will be discussing in the coming slides. And there are several algorithms, the classical algorithms based on this discrete log problem, and the different classical attacks for this. And elliptic curve discrete problem is a third class of problems where the classical cryptographic algorithms rely upon. Next slide, please, sir. So now we have understood that we need extra mathematical things to understand the classical methods, the classical cryptographic methods. So the first thing is that we need to know about this modular arithmetic. Those who are familiar with the modular arithmetic, it's a simple thing, but just for a beginner, I just want to say that this modular arithmetic, it wrap around the integers after reaching a certain value. For instance, I'm talking about mod 5 arithmetic, right? Mod generally stands for the remainder. So mod 5 arithmetic means what is the number that is left out when a number is divided by 5. So the remainders would be 0, 1, 2, 3, 4. Beyond that, we will not get an answer. You will not get the number, is it not? So therefore, the integers are wrapped around these 5 digits. So that's what we mean by this modular arithmetic. So for instance, I have a nice example. 17 is congruent to 5 mod 12. So when do we say that this relation is true? Is when 17 minus 5 is divisible by 12. Yes, that is true. So therefore, this is how we write down the modular relation. This is one arithmetic one have to have good familiarity to understand the second class of algorithms. Yeah, so now we are into this quantum algorithms, as the previous speakers have pointed out. Short's algorithm, Grover's algorithm, they have posed a threat for the existing classical algorithms. So that's the reason why we are now here to understand what math is required for the PQC. Next slide, please, sir. Yeah, so these are the 6 different approaches as mentioned by Professor Harvest. These are the different approaches, and we will focus on this lattice-based cryptography. For that, we need to know some terminology, so which I'll be taking up now. Yeah. So there is a connection between basis and lattices. That is the reason why I introduced what a basis is in the beginning of my presentation. They're connected in the sense that the basis is any combination, any linear combination of linearly independent vectors, but your lattice is going to be a set of integer linear combinations. Here also it is a combination, but the combinations would be integer linear combinations. Moving on to the next slide, we have an example. Right. Suppose if I have taken the base vectors as 1, 0, 0, 1. All linear combinations of them have generated the entire of R2, right? But then if I restrict the coefficients to be only integers, I mean, I'll write it as alpha v1 plus alpha v2, right? Alpha 2 v2, right? If alpha 1 and alpha 2 both are integers, then we say that whatever structure that is formed is a lattice. And then please click on the answer. So we have a square grid. If if the base vectors are 1, 0, 0, 1, we get a square grid like this. And then if it is an alternative basis 1, 1, 1 minus, we have a tilted grid. So this is completely different from our R2. I mean, if you take a general linear combinations, it would be the entire of R2. But if it is the integer combinations of it, we would get grid-like structures like this called lattice. Next slide, sir. Yeah, so why lattice is because there are 3 fundamental lattice problems which are NP hard. And most of the post-quantum cryptographic algorithms, or I should say whatever I'm taking up in today's lecture, are based on these 3 NP hard problems. The first problem is the shortest vector problem. What is the shortest vector problem is? We have a lattice. The problem is to find out the shortest non-zero vector in that lattice. Right? That is the problem. Very simple to state, but very difficult to solve. Let's move on, take an example. For instance, suppose if I have a lattice which is generated by the vectors 3, 1, 2, 2, right? The length of B1 is root 10. The length of B2 is root 4 plus 4 root 8, right? And if I want to find out what is the shortest vector, right? I can simply find B2 minus B1, and it is giving me the vector minus 1, 1, whose length is root 2. Of course, this is shorter than the previous 2 vectors. But this need not be the only answer, right? You have to find out, are there any other possible vectors which are of shorter length? So that's not very easy to find. And as I said, this is an NP hard problem, and no polynomial time classical algorithm is known till now. Yes, sir. Next problem is CVP, closest vector problem. So the problem is to find out the lattice vector closest to a given target vector. The vector would be outside the lattice, and then we have to find out the vector within the lattice which is closer to that. That is a problem. For instance, here I'm looking for t is equal to 2.51. That's a vector outside the lattice. You cannot generate, you cannot find out integers such that t is equals to alpha b1 plus beta b2. That's not possible. So this is outside. And if you just see, the slide gives you a nice answer for that. It's saying that the closest lattice point is 2, 0. So this is the second NP hard problem. Yes, next slide, sir. The third problem is the shortest independent vector problem, SIVP, where we have to find out a set of linearly independent vectors which are of shorter length than the one that you have already taken. So here again, I'm just looking at the length of the vectors b1, b2. And if I look at the final vectors minus 3, 2 and 1, 3, you see that minus 3, 2 is shorter in length compared to the first set of vectors. So identifying such a set is also an NP-hard problem. Yes, Professor. Next. Next slide, please. Yes. Next slide, please. Yeah. So now we are into this Kyber dilithium algorithms, and both these algorithms are based on this lattice-based problems. You will understand that SIVP plays a very key role in this algorithm, and moreover, it is module-based arithmetic. So we will just understand a little, more about the mathematics related to this. Yeah. So the basic mathematical concepts that are related, the related concepts are SIVP, as we already discussed. It is shortest independent vector problem, and SVP, shortest vector problem, and via this LWE. So this is yet another mathematical problem that we have to understand to actually have a good idea of this PQC schemes. And my next slide introduces you to this LWE. So what is this learning with error problem? What is this is? All of us know how to solve a system of equations, right? Suppose if I give the equation AX is equals to B, you have very good classical methods to give the answer. But what if I add some small, I should say, error term or a vector with very small magnitude? I'm just giving it a rough sense. So if the E is an error vector which has a magnitude something like 0.1 or whatever it is, right? So if I introduce a vector like this and add up, so then this problem is hard to solve. That means if I know A, if I know E and known P, finding S is almost, it's a very hard problem. So this particular problem is what is called LWE, learning with errors, and that is one of the basic mathematical things that this Kyber is based on. Next slide, sir. And in addition to this, T is equal to AS plus E. Suppose if I use modular arithmetic, that means the addition I'll take with respect to a module Q, and this multiplication also, if I do that, then this problem comes out as ML-WE module learning with error. Yes, Professor, next. Yeah. So now what is a KEM protocol? Already the speakers have explained you the basic idea behind this KEM, where you have three important steps: key generation, encryption, and decryption, or encapsulation and decapsulation. Right, and the basic, if you see the mathematical statement, if you see for the key generation, they simply use this LWE or ML-WE format. T is equal to AS plus C, right? And for encryption, Bob or Alice, whoever takes the lead, they will calculate the UNV, the ciphertext, sends this ciphertext, and then they do what is this decryption to get the answer. So all this time we have seen that this matrix A or vector C that we were working on were all simple numbers, right? You had a matrix 1, 2, 3, 4, something like that, or a vector could be 1, -1, 5. Its length could be 256 or 2, whatever it is, but then it was all numbers there. But then the next important thing in this next slide, sir. The important thing in this Kyber algorithms is that all these matrices and all these vectors are not simple scalars, but they are polynomial rings. Okay, it is something like you could have a polynomial, something like x square plus 1, a matrix with entries as x square plus 1, x square minus 7, 2x plus 3, something like that. Okay, so each and every entity in this matrix, or each and every entity in the vector, would be a polynomial ring. So all of us are familiar with polynomials, but what is this polynomial ring? So that is what we'll take up now. Yeah. So working on polynomials, the basic standard multiplication, standard addition, all of us are familiar with. But some things we have to make notice whenever we are multiplying two polynomials. See, so for instance, one polynomial is of degree 2, the other polynomial is of degree 3, and we multiply. The answer is a polynomial of degree 5. So the degree of the polynomial increases when you multiply, and of course the coefficients also may grow. Like, right? Suppose if I have 3x square and 10x square, it becomes 30x power 4. So that is a major thing we have with the standard multiplication, right? And then what the modular arithmetic does is that this, when I take up the multiplication modulo, say some 5, right? All the coefficients will be less than 5. So that means the coefficients get reduced whenever you use modular arithmetic, but still the degree will be increasing, right? 2 into 2 becomes x square into x square is x power 4. So therefore we have what is this ring based arithmetic, where the coefficients are reduced modulo q, and also the degree of the polynomial is reduced. For instance, suppose if I say x power n plus 1, okay, degree reduced modulo defining the polynomial, say it is defined by x power n plus 1, then every term in that polynomial will be of degree less than n. That means you have at most x power n minus 1 term appearing it, or the power of x power n minus 1 appearing it. So that is the reason why the entire Kyber algorithms, Kyber as well as dilithium, are based on ring-based arithmetic. So you can just have a quick look at this modular arithmetic, where if I have taken modulo 5, each after performing the multiplication, every coefficient is less than 5. Next slide, please. But the power was 4. Just notice that. But when I use a polynomial ring structure, what happens is the power of the maximum power of x that you would get with this x power 3 plus 1 description, you will get it as x square. Okay, so that is how the degree of the polynomial also gets reduced. Next slide, please. You have a nice example here where you see the power, the maximum power of x that you get is x square after multiplication. And not only that, the coefficients are also very small coefficients, because we have taken modulo 5 arithmetic here. Yes. Next slide, please. Right. So now let's quickly look at the mathematical basis. Some of these things are already discussed. So this Kyber is based on the module LWT problem, and then your n is fixed. This n stands for the degree of the polynomial that you would permit. Like the degree of the polynomial will be 256 minus 1, 255. That is the maximum degree of the polynomial that you permit here. And then we take a modulo 3329 modulo, right? And then these are the 3 important steps: key generation, and then yeah, we have discussed about this little earlier also. Next slide, please, sir. We have encapsulation, decapsulation. But remember that your E1, S1, all these are polynomials now. That's the only thing that we have to remember. Rest of the process is similar to other techniques as well, other encoding, decoding techniques. Yeah. So this is an example for Kyber over Z5 x square plus 1. We have a public matrix. Alice has a secret key 2 plus x. Right? And then suppose E is equal to 0, she generates T is equal to AS plus C, and then sends this to Bob. In the next step, Bob uses this T. And then if 1 plus X is a message that Bob wants to send to Alice, he nicely chooses S prime E1, E2, calculates the ciphertext, and then shares the ciphertext to Alice. Next slide, sir. And then yeah, so M is equal to at the Alice ends, she nicely has 1 plus X. So this is all modular arithmetic that has been used to get the encoding and decoding done. Right. So these are some of the variants that we have in KEM 51276811024, and then the decapsulation failure rate is also mentioned here. It's very less, indicating that we are very sure with high probability we can I mean, this decapsulation process would be a success. Next slide, please, sir. Yeah, so these are the library and tools that are available. Maybe if you are interested to work on the algorithms that Professor Prakash has suggested, so maybe you can use these tools to work on this Kyber related algorithms, Kyber as well as DPT. Next, Professor, next slide. Yeah, so now we are into the digital signatures theme, or where I'll be discussing about this dilithium lattice-based post-cryptographic algorithm. Next slide, sir. Yeah, so the key concepts is almost similar to what we had for Kyber. So I will not go into the details of the thing, but only one important thing is that instead of T is equal to A S plus E, which is an error, now we have T is A S1 plus S2. Of course, S1 and S2 are to be taken as small vectors, and the mathematics behind this particular algorithm is also same as Kyber. So I'll not be spending time on this. So just let's quickly look at an example of this example, and then yeah. So this is an example where again I'm working on this Z file, right? And then we have a public key, we have a secret key, we have generated what do I say? The public key as 2 plus x 1 plus 3x. Next slide, please, sir. With yeah, the message HI, how do I encode decode it? So we have this hash, as already Professor Prakash has pointed out. So we'll have a hash here, we'll be using this, and then we'll generate a signature. Next slide, please, sir. And then the verification process goes, and finally, yeah, finally if it gets verified, yes, the process is complete, right? So these are some of the variants that we have, right? And then moving on, I think I'm done with my slide. Yeah, so these are some of the references that okay.
Yeah, I think with that we'll bring in Baw. Baw, go ahead.
Okay,
on the
you,
AI/ML
Prakash.
and PQC.
And
Yeah.
yes, thank you. Okay, we are like 12 minutes away from the advertised stop time, and I do want to respect people's time. So to be fair to people who have a hard stop at 2 o'clock Eastern time, if anybody wants to start asking questions or you know, questions and comments that you can't wait to get off your chest, please feel free to do so now. If nobody wants to ask a question, nobody has a comment, then of course I can keep going with the slides. And by the way, please check out the chat window, because I've posted in the chat window all the relevant links that has been mentioned, and especially if people want to ask about whether there'll be recordings and slides, whether those will be made available. I posted a link there as well that you can check back in a week. It takes us a few days to a week to get those ready, so there's a link there you can check in a week and to get the recording slide. Okay. Okay, seeing that there is no questions and nobody wants to ask a question right now, so I'll just talk to the slides. Okay, so now we're at this part where we contemplate about what AI/ML and PQC might do together, what's the interplay between the two. So if I look at the 2024 edition of the AI/ML International Network Generations Roadmap, the way we think about it is when we look at AI/ML and the network, we look at the possible relationships, right? One is where you can adapt the network to support AI/ML workloads. Or you can turn it around and say, let's use AI/ML to improve the network, right? Or you can try to integrate the two very, very tightly, commingle the two, and see if we can make something new out of it. So that's the focus, the option C at the top right corner of the slide, right? Commingle AI/ML and the network, make the network itself intelligence. So that's the focus of the 2024 edition of the AI/ML chapter of the International Network Generations Roadmap for 2024, right? Now, if I try to use the same framework to look at AI/ML and PQC, again, I can say, okay, we can look at how do we use post-quantum cryptography to secure AI/ML, and think about security assets, securing the infrastructure, or we can think about using the AI/ML to improve post-quantum computing, post-quantum cryptography, Or maybe we can think about how to integrate the two very, very tightly together and see if we can make something new out of it, right? So that's the big framework about how to think about these things. Next slide, please. So on the first option, use post-quantum cryptography to secure AML assets and infrastructure. Now this one, at least in my mind, turns out to be fairly straightforward and fairly simple, right? So what do we secure with this? The things that we can secure when AML is involved, we can think about securing the data, securing the model, thinking about securing the computing hardware, securing the communication networks, securing the database, etc., etc. And it doesn't really look that much different from securing other general computing assets and general computing infrastructure. So in that sense, you can say, okay, what's the big deal? And the answer here is it's probably not a lot of a big deal. You're just securing AML-related stuff, just like you secure other general computing stuff using post-quantum cryptography. The interesting thing might come up when we talk about homomorphic AI for privacy preservation. So homomorphic AI talks about doing AI inference or AI-related computation in a way that doesn't even require the computing server to decrypt the information, right? You send encrypted information to the AI server. The AI server, without even decrypting it, can manipulate the information and send it back to you. Okay, that's not what we mean by homomorphic AI. And this happens to be a specialty of Dr. Sear, one of our panelists here. So if Dr. Sear says anything about homomorphic AI that is not the same as what I'm saying, I defer to Dr. Sear. I hope you're listening. Okay, so that's homomorphic AI. That may have something interesting there. Special quantum advantage. Well, one thing that general classical computing don't quite have is this special ability to detect eavesdropping, okay? So in classical computing, classical network, classical communication, you send a message, somebody read the message in transit, make a copy of it. The receiver may not know anything about it at all. But when it comes to quantum communication, this is impossible. If somebody observes a quantum state, that observation, the act of observing it will change the state itself. So that means when you do quantum communications, eavesdropping is almost guaranteed. So somebody eavesdrop on you, you wouldn't know about it. It will change the quantum state and the receiver will know about it, okay? So this may be something new that can be taken advantage of later, right? Next slide, please. So, and then, okay, what can we do if we say we want to use AI/ML to improve post-quantum computing instead? Well, what is there to improve? Are we talking about are we trying to use AI/ML to improve the PQC algorithm themselves? I put that in yellow because I don't think that is very likely. Not to say it's not impossible, but I don't see a lot of work that says, okay, use AI/ML to very directly improve the algorithms themselves. Okay, but I do see many papers, many works, many research efforts trying to improve post-quantum cryptography systems, not on the algorithms themselves, but on other things that make up the system. The implementation aspect, the system integration aspects, the deployment aspects, and the application aspects of post-quantum cryptography. Okay, so there's certainly many efforts in using AI/ML in threat detection. This is not PQC specific, but this is applicable to systems that use PQC as well. So there are works that uses quantum machine learning and quantum deep learning for network threat detections. There are eavesdropping detection. And again, when it comes to threat detection, we do have a new tools with quantum communication, which is, it's really good ability to detect eavesdropping, okay? Again, using quantum eavesdropping detection is not specific to AML, but it definitely can be leveraged by AI/ML systems to improve eavesdropping detection, right? Now, and then more popularly, more efforts is being exerted to using AML to deal with side channel attacks. Okay, I give you a couple examples here, right? One is to use deep learning assisted power analysis. So one way of doing side channel attack is to look at the power traces, the power usage of a system when they do computing. Okay, so when a computing systems processes cryptographic matter, depending on the computation, it may consume different amounts of power. Right? So just by looking at the power use, the use of power, the power traces, you might deduce information from that. So with that, and people have tried to do that to attack post-quantum computing algorithms as well. And I give you a couple of references there. Where a team in Sweden uses that and demonstrate that yes, you can use machine learning to improve the attack, the side channel attack, when it comes to dealing with post-quantum cryptography, post-quantum algorithms. Okay, so there's a YouTube video, a link to a YouTube video there where you can look at the presentation given by that team, and you can also read the paper. There's a link for it as well. Another example has to do with rowhammer attack. So rowhammer attack, again, is used on classical cryptography as well. It's not specific to quantum computing, but people has demonstrated that it is possible to use rowhammer attack against post-quantum computing and recover the information, key information, using rowhammer attack. So for those who are not already familiar, rowhammer attack refers to the act of very frequently access DRAM rows adjacent to the rows that would use to host other information, the thing that you want to attack. Okay, so that's rowhammer. Again, I give you references to a couple of papers there if you want to look at the details. And then we comes to post-quantum key distribution, or just quantum key distribution parameter optimization. So as we go to post-quantum key distribution, it gets more complicated. Okay, the key sizes are larger, key rates are larger, security levels, you have multiple security levels. So there are multiple parameters, even without modifying the underlying algorithm themselves. You can choose how you use the algorithms, right? You can choose different block sizes, you can choose different refreshing key rates, you can choose different security level, different noise tolerance levels, since when it comes to noise quantum computing, noise is a big issue. The lower the noise tolerance, the harder it is to do. So different optimization, different parameters you can optimize when it comes to doing key distribution. So this is where quantum machine learning is helpful. At least I found, I've read papers and works that demonstrate that quantum neural networks, quantum reinforcement learning, etc. These are helpful in helping systems optimize different parameters, even without tweaking the underlying algorithm themselves. You use quantum machine learning to figure out, the parameters to optimize, block sizes, key rate, security level, etc., etc. Okay, next slide, please. Okay, then when it comes to tightly integrating or commingling AI, ML, and post-quantum computing, this is a more speculative and open questions. I haven't actually seen work that directly addresses this. As a personal opinion, I believe that there is potential in this area when it comes to homomorphic computing, homomorphic AI, where you try to perform AI manipulation without decrypting the message itself. Okay, so the good news is most homomorphic algorithms that we know about are all based on some kind of lattice math. So it's a very good chance that they're all already quantum secure or quantum resistant, but there's no guarantee there. I do give you a reference here to a paper that talks about homomorphic AI, quantum delegated and federated learning via quantum homomorphic encryption, which may point a way towards a more tightly commingle AI, ML, and post-quantum computing. So, but I see that as an open space for innovative research in that area. So if you're looking for a PhD topic that involves AI and quantum computing and post-quantum cryptography, this might be a good place to look. And this happens to be Dr. Siet's homomorphic post-cryptography happens to be Dr. Siet's specialty as well. So now, seeing that we're at the advertised stop time, I will stop talking now and return the floor to Dr. to Prakash.
Yeah, thank you very much, and I appreciate all the efforts. Even though we are delayed, but we have tried to complete the completeness of the recording. And here are a few questions which generally I have had. Just it's a yes/no types, most of it. So few of them I can read, and maybe some of you can answer just for the recording, so that we have. So what do we need? Why do we need post-quantum cryptography now? The question is it now or later? Anybody wants to answer from panel? Why do
Okay,
we need it now?
Okay, okay. So we need it now because of the harvest and decrypt later practice. Okay, so it takes time for people to upgrade all the infrastructure and the software and the systems such that they employ post-quantum cryptographic algorithms. It takes time, a lot of time, depending on how big and how complicated or how expensive the systems are.
Super.
But
So
you need to get there before you can even secure your assets to be quantum resistant. So you need to start having the cryptography. You need to start having the algorithms now, so you can start, at least for the things that you secure at rest. You want to secure them now with PQC, so that you don't worry about people just hacking in, grab it now, and worrying about decrypting it, 10, 15 years from now.
fantastic. So the 7-year limit is there, financial record. So that's one of the reasons. And 35 is what federal recommends. And each country will have its own, what to call the level and timing. Next, going to category and subcategory. This I'll just answer. These are computer and cryptography is the category as far as Federal Information Processing System is there. For the DPI and PKI, are they same, different? What anybody, any comment on that? Because DPI is the term used in the UN terminology, whereas PKI is the existing infrastructure. Any comment on PKI with respect to PQC? So just mention that PKI is the infrastructure which is used currently by the most of the countries. Then going to one last question here. Is in cryptography ciphertext is the result of encrypting the plain text, a form of scrambled unreadable data that protects sensitive information from being understood by. Now, is it authorized individuals or unauthorized individuals? Which is, in this case, I have said authorized individual. Is it true or false? Obviously, reading that is harder, but only unauthorized we want to prevent. Okay, authorized people we don't want to prevent. That's all. And
it becomes a matter of how do you define authorized? If you define authorized as the person with the proper and decryption key, and then by definition, only authorized people can read it.
Correct. Makes sense. So I think I will, one last one, I'll just, are the IPR waived for FIPS 203, 204, 205 by standards by original IP holders?
Okay, seeing that no one else is answering this one, I also do not have the answer right now.
Yeah, I have the answer.
Okay.
It is yes. It is yes, because the standards, if you participate and if you use, then the parties that are involved have to, and they have waived. So there is no question about this is open. You can use it as long as you have it depends on which region you are from and what waivers are there. But most of them have accepted the waivers. So all the contributions are waived and they can use. So therefore there is no restriction on using it. But the question is, what procedures you follow? Each country may have a different procedure with the same standards. So that could be the thing, but IPRs are all waived. I think that's all for the day. I think we will close it here because I know it is beyond time, but at the same time, we don't want a half and the start was delayed, etc., etc. So I apologize. Next one is coming is QKD, and that we will plan out as we announce. At this time, it is in the announcement stage, and we'll get there in another 14 days, possibly. Okay. So with that, I will thank all the audience for patiently waiting for us to let you in, as well as our panel, which had to shift to get there to stop the earlier errors which he had. And next time we'll just do it as a meeting, not webinar, to avoid this. With that, I will stop the recording and hopefully that should stop recording. Yeah, I'll stop.